In this video, we're going to talk about energy, and I'm going to start by posing a question to you, a little bit of a mystery. So let's say you're studying a roller coaster, and what you're interested in studying is how your motion changes as you go down the first big hill. So here's our roller coaster car at the top of the first big hill, and it's going to roll down the hill. And what you're interested in knowing is, can you figure out how fast the car is going to be going when it's at the bottom of the hill based on what you know about what it's doing at the top of the hill? So why might answering questions like that be hard? And if you reflect on the types of physical quantities that we've discussed so far in class, things like accelerations and velocities and forces, you see that one of the complications here is that these scalar quantities, because they have a magnitude and a direction, are going to be hard, really hard to track as the car rolls down the hill, because as the car is rolling down the hill, its direction is constantly changing because the hill is curved. So near the top of the hill, the car has a velocity vector that looks something like that, and then halfway down when it gets here, its velocity vector has changed, and when it gets to the bottom, its velocity vector has changed again, so that this velocity vector is constantly changing direction. That can be really hard to track. So solving a problem like this, we're going to have trouble if we try to rely on the things that we've used so far: velocity vectors, acceleration vectors, force vectors. So we need another tool. So let's talk about energy and see how energy is going to be this tool that helps us solve problems like this. So the first thing that's going to help us out is that energy is not a vector quantity. Energy is a scalar. And so we lose some information. We lose some information about direction. But by allowing ourselves to lose that information, we gain a lot of power in the types of problems that we can study. So energy is just a scalar quantity. One way you can think about energy is a summary of the state of a system. So what I mean by this is that the quantities that we calculate and call energy reflect things like the position of a system, the velocities of parts of the system, and also the masses of parts of the system. So this energy number, these numbers that we're going to calculate, which are energies, are summaries which encapsulate properties of the system, many properties of the system: positions, velocities, and masses, all simultaneously. But before we get too far, let's talk a little more about what energy is in a physical sense and how we can go about quantifying how energy flows through systems. So I use that term flows because energy is really a nebulous concept. It can be really hard to understand what exactly energy is. And one of the reasons for this is that we only are really aware of energy in a system when that energy is changing forms from one form into another. So for example, chemical energy being converted to heat energy by burning a piece of wood, or a type of energy called potential energy being converted to the energy of motion, which is called kinetic energy, when a mass, like a rock, falls from a high height to the ground. So we're going to begin by defining a physical quantity called work. And work is defined as a force that's exerted over some distance or over some displacement. But more fundamentally, what work really is work is the act of energy being transferred to or from an object by means of a force that acts on the object. So when a force is exerted on an object, that force has the capability or the possibility of doing work on that object. And what that means is that work changes the energy of that object. It transfers energy to or takes energy away from that object. So another way of thinking about this is forces, these things that we've been studying for a while, are the means by which energy is transferred from one object to another. All right, so the way I've written out work here mathematically is I've written work equals force dot d for displacement. And so this dot between the f vector and the d vector, it looks like it's multiplication, but it's a little bit different than that. What I'm actually doing here is this is a vector operation called a dot product. So let me explain what the dot product is and how you calculate it, and then we'll talk about why it's necessary. All right, so I've drawn an object, this little ball right here, and let's imagine that this object is experiencing a force. There's a force exerted on it that's sort of up and to the right, like this, and that force is being exerted on the object as it's moving to the right and experiencing this displacement represented by this vector here. So the meaning of the dot product is, so I stepped away for a while, now I'm back, I forget where I was talking about work as the dot product between a force applied over some displacement. And so consider this force vector F and this displacement vector D, and the dot product, what it means graphically or geometrically is it's the product of the magnitude of the displacement and the magnitude of the force vector that is in the same direction as the displacement vector. In other words, the force can be exerted, but only the force that is exerted in the portion of the force, the component of the force that's exerted in the same direction as the displacement does work on the object. So I've labeled that here in the magenta F with the perpendicular, I shouldn't have done that, F parallel. It's the portion of the force that's parallel with the displacement. Another way of saying this is it's the product between the displacement and the projection of the force onto the displacement vector. And so this is a weird term, but one way you can think about it is if there were a light up here shining down on the force vector, it would cast a shadow on the displacement vector, and it's that shadow, the length of that shadow, that is the important thing. So another way to compute the dot product is you see that if you call theta the angle between the force vector and the displacement vector, then the projection of F onto D, or the portion of the force vector that points in the same direction of D, is F cosine theta. So the dot product, F dot D, is the same as FD cosine theta. Okay, so now let's consider a special case of a force exerted on an object. Let's say it's a car that's moving in a straight line, and the force is exerted in such a way that it lines up with the displacement. So there's the angle between the force vector and the displacement vector is 0 degrees. Cosine of 0 is 1. So that dot product just simplifies. It just goes away to the product between the magnitude of the force vector and the displacement vector. And let's see if we can connect this concept with work with some of the other things that we know about, such as mass and velocity. Okay, so here's that car. It's moving along a flat surface, and there's a single force, no friction, nothing like that. There's a single force that's exerted, applied to the cart, and causing it to move to the right. So of course there's a normal force and the cart has a weight, but those two forces, one points up, one points down, they're going to cancel each other out. So there's one applied force that's pointing to the right. The net force is equal to this applied force, and that's equal to the mass of the cart times its rate of acceleration. And the effect that this force has is it causes the cart to accelerate from some initial speed v1 at its initial position x1 to some other velocity v2 at position x2. So the force causes an acceleration, the velocity of the cart changes, and its position changes. So it experiences this acceleration and a displacement at the same time. So let's see if we can use kinematic equations of motion to calculate the change in velocity, and then connect that change in velocity with the acceleration and the work that's done on the cart by this net force, and see what we get. All right, so we're going to use one of our kinematic equations of motion that looks like this, and it says that v2 squared minus v1 squared equals 2a times the quantity x2 minus x1. Now we can write x2 minus x1 as the displacement. It's the distance traveled. Everything's in 1D here from x1 to x2, and so we're going to do that. And let's write out the work done by this force, this net force. The work done is the dot product between the force vector and the displacement vector, or FD cosine theta. And here, of course, the angle between these two vectors, f and d, is 0 degrees. So the cosine of 0 degrees is 1. So that goes away. All right, we wouldn't have had to do that, but it just makes the equation simpler here. In other words, we could have considered a more complicated case where the angle between f and d is not 0. But let's go with the simple case for right now. And of course, force, Newton's second law, the net force is equal to mass times acceleration. So we can plug that in for F over here. So now what I'm going to do is I'm going to solve the kinematic equation for acceleration. And I'm going to plug that in for acceleration in the work equation and see what we get. All right, so acceleration is 1 over 2d times the quantity v2 squared minus v1 squared. And let's plug that in for a in the work equation. And what we get is something that looks like this. And so here I'm going to add a little net subscript to the work, because this is the net work, because here, or the total work that's done on this cart, because here we're considering a special case where there's only one force. The net force is this one force that's accelerating the cart to the right. And so we get at this equation where the total amount of work done on the cart is equal to this quantity that depends on the changes in velocity, or sorry, the changes in the velocity squared, and the mass of the cart. So I'm going to factor this out and write it a little bit different, and we'll see what we get. So I've distributed out the 1/2 m, and so I get this formula where the total work is equal to 1/2 m v2 squared minus 1/2 m v1 squared. So the total work done is the change in this quantity, which is given by 1/2 mv squared. Well, it turns out that change in that quantity, 1/2 mv squared, is a change in the energy of motion of the cart. This quantity is called kinetic energy. Kinetic energy, or energy of motion, is defined as 1/2 mv squared, where v is the speed of the object. Again, this is energy, so we've lost information about direction. Energy is just a scalar quantity, so kinetic energy is also a scalar quantity. Okay, so let's summarize some of the stuff that we've just discovered. We've discovered that kinetic energy is 1/2 mv squared. We've also discovered that the total work that's done on an object is equal to that object's change in kinetic energy. So this relationship is called the work energy theorem. And I'm going to call it work energy theorem version 1.0, because we'll see that it's important, but it's not complete. We can think about the work done on the object when there's many forces involved, and then the sum of all the work done by all the forces on the object is what we've written down right here, the total work, and that's equal to the change in kinetic energy. But we'll have more to add to this. Okay. So writing this out a little bit more, the total work done on an object is the net force exerted on the object dotted into the displacement of the object, or the dot product between the net force and the displacement of the object, and it's equal to kinetic energy. So what's interesting here is the quantities on the left-hand side of this equation are vector quantities. The quantity on the right-hand side of this equation is a scalar quantity. Well, another name for the dot product is the scalar product, because what happens is when you take the dot product between two vectors, the result is a scalar. It's the product of the magnitude of one of the vectors and the portion of the other vector which points in the same direction as the first. Okay, so remember the mystery, the problem that we're going to be trying to solve in this unit is how can we study the motion of objects along curved paths like this without using vector quantities? Because vector quantities will be really hard to track. The direction is constantly changing, the magnitude is constantly changing. You know, so the quintessential roller coaster problem. How can we study the motion of a roller coaster along its track? So we have a piece of the puzzle, and one of the pieces of the puzzle is, instead of thinking about forces and displacements and velocities and accelerations, we think in terms of energies instead. We think in terms of the scalar quantities energy. So at every point on the track, the roller coaster up here has an energy. Here it has an energy. Here it has an energy. And that energy that the cart has is going to tell us information about the way the cart is moving, its velocity, or more correctly, its speed, because we've lost information about its direction, and its position along the length of the track. So we have a piece of the puzzle, but we're not quite there yet. In order to understand this, in order to be able to study and make sense of this entire roller coaster problem, we're going to have to talk about another type of energy called potential energy and add that to what we know about kinetic energy. And those two pieces together will allow us to study problems like the roller coaster. So that's coming up in the next lesson. But before we end this lesson, let's look at the dot product again a little bit more carefully, and let's look at what happens, or how you calculate a dot product when you have your vectors written in unit vector notation. All right, and just for the case of simplicity, let's consider the situation where we have a force vector and a displacement vector, which are each two-dimensional. So there's an x component, a y component, but there's no z component. All right. So let's consider the dot product between a force vector, which looks like this, and a displacement vector, which looks like this. So obviously, each of these vectors has an x and a y component. So let's say F equals 7i hat plus 6j hat newtons, and D is 9i hat plus 4j hat meters. So one way you could proceed is know that the dot product between F and D is FD, the magnitude of F, times the magnitude of D, times the cosine of the angle between F and D. But here, the angle between F and D might be hard to find, and we don't have to do that. Okay, let's think about this in terms of pieces. Remember that the meaning of the dot product is the product between one of these vectors, D, and the projection of the other vector, F, in the same direction as D. Well, if you think about this a little bit more carefully, when you have these vectors written out in unit vector notation, you've already broken up the vectors into x and y components. In this case, there's no z component, and so the x component of F is already aligned with the x component of D. So you can simply multiply those two numbers together to give you the total contribution to the dot product along the x dimension. 7 times 9 would give you the total contribution of the dot product in the x direction. And in the same way, 6 times 4 would give you the total contribution to the dot product in the y direction. And you just simply add those two numbers together to give you the result. So the dot product between this F and D would be 7i hat plus 6j hat dotted into 9i hat plus 4j hat. And what I'm saying is this dot product is equal to 7 times 9 plus 6 times 4. And the units would be newtons times meters, or newton meters. So that's 87 newton meters. Well, another name for a newton meter, this combination of the unit newton for force and meter for distance, is the joule. So newton meters are units of force, or sorry, Newton meter is a unit of work. It's also a unit of energy, and an alternative unit of energy is the joule. 1 joule equals 1 Newton meter, and the joule is abbreviated J. So joules are the SI unit for energy. And so when we talk about a kinetic energy, the energy of motion, we'll report that in units of joules. Later when we talk about potential energies, those will also have units of joules. All right, so this concludes this lesson, this video lesson on kinetic energy and work, and the first version of the work energy theorem. Review the slides posted on this topic. There's more information there, and work on your homework. All right, till next time.